Okay, let us continue to the test number 4. The question is that a projectile is fired in such a way that its horizontal range is equal to 3 times its maximum height. What is the angle of projection? Okay, so we have a projectile. Okay, fire in let's say the angle theta. Okay, and we have that the length of the projectile is 3 times of the height h. Okay, so we have r is equal to 3h. Okay, now from previous work, okay, we have this relation. That relate the initial velocity with the height. This is a component of the initial velocity in vertical direction, and the height like this. So we can say that h is equal to vy0 square over 2g. And here you can see that if we dissolve the initial velocity into vx0 and vy0 from the initial velocity v0, we have that vy0 is equal to v0 sine theta. So we have v0 sine theta square over 2g is equal to h, which is equal to if we multiply by 3, we will get the length of the projectile. Okay. Now for the maximum height, for the length r. Okay, we want to calculate the length of the projectile. Since there is no acceleration in the vertical direction, so we know that r is equal to vx0t, where vx0 here is a component of the initial velocity in the x direction, and t is the time of flight. It means that the total time that this object moves from start to the end point. Okay. Now if we can calculate t, we can get r. And how can we calculate t? You can see that the more we can separate this motion into the x component and y component. The x component, the velocity in the x component is a constant since there is no acceleration. So it means that the object can move in the horizontal direction indefinitely. It can continue move in the horizontal direction until it reaches the ground. And what the y direction, the motion in y direction will give us the time that the object stops moving, because It will stop when we look at the vertical direction. The object moves up and then down, and when it reaches the ground again, the particle will stop. So this time t is the time that the particle moves. If we look at the vertical direction only, it go up and then down. Okay, so we will look at the vertical motion again by using the equation, the formula y is equal to y0 plus vy0 t. Now we use the acceleration is equal to minus g, so we have minus g half of gt squared. This is because we use the upward direction as a positive direction, so the acceleration point downward, so we have the negative sign here. Okay, and we know that the initial position in y direction is 0, so we have y0 is 0. And we want to know the time that the particle moves back to the ground again. So the final position of the particle in vertical direction is 0 also. So we have y0 here. So we have 0 is equal to vy0t minus half of gt squared. Or we rearrange this equation, we get vy0t equal to half of gt squared, which gives us that t is equal to 2 vy0 over g. Or we can write the vy0 is this vy0 is v0 sine theta, okay, over g. So now we have the time of flight, okay, and when we put this to this equation and use vx0, we can write vx0 as a v0 cos theta and time t. Okay, this is the x component of the initial velocity. Together with this equation, we have r is equal to v0 cos theta time t, which is 2 v0 sine theta over g. Okay, and we put this r into this equation and also h into this equation. So finally we have 2 v0 square cos theta sine theta over g, which is r, right? This is r, equal to 3 times of h, which h is equal to this term. So it's v0 square sine square theta over 2g. Okay, so you can see that we can eliminate some term. v0 square is gone, sine theta, this term we eliminate the square, g is gone. So if we rearrange this sine theta over cos theta, which is equal to tan theta, or can write sine theta over cos theta, which equal to tan theta, is equal to 4 over 3, which gives us that theta is equal to 35.1. Okay. satisfy part 1, and the solution is D. Okay. So that is for the question number 4. Okay, let's go to the question number 5. Question number 5 asks that if there is a person standing at the top of a hemisphere, half sphere or hemisphere, half sphere, half spherical rock of radius r kicks a ball initially at rest, okay, on the top of the rock to give it horizontal velocity vi, okay, the initial velocity vi as shown in the figure. What must be its minimum initial speed if the ball is never to hit the rock after it's kicked? Okay, it means that the ball will fly like this in this part, and it will never hit the rock before it hit the ground. Okay, how can we solve this problem? It's straightforward to solve this problem. That is, if we know the surface of the hemisphere, okay, which is the part of a sphere, and then if we know the part of the ball, okay, which we know that the trajectory of the part of the ball, the motion of the ball is a projectile, which the trajectory of the part of the ball is parabola, okay, and if we can get the condition that the height of the ball at the same horizontal position is always higher than the height of the rock, okay. If we have the condition that the height of the ball follow this trajectory is always higher than the height of the rock, and from that condition we can say that the ball will not hit the rock after it's kicked on the top of the rock, okay. So it means that we have to write down the trajectory of the ball and the surface of the rock and compare that two function, okay. For the ball, okay, first let's say from the ball we have that if we write the vertical position of the ball, we can use this formula, that is y is equal to I0 plus vy0 t minus half of gt squared. Again, in this case we use the upward direction as a positive direction, so we have the minus sign here, okay. The ball starts its motion at the top of the rock, so we know that R0 here is equal, Y0 here is R, and it starts from less, so it means that we know that Vy0 here is 0, okay. So this is the equation to obtain the vertical position of the ball, okay. Or we can write it as y is equal to r minus half of gt squared. Please note that this r is not the range of the motion. In this case, r is the radius of the half sphere log. This is the radius, not the range as in the previous question. So here we use r as the radius. Okay, and we have y, the vertical coordinate of the ball. What about the horizontal coordinate? Okay. They say that initially the ball is at rest and then this guy kick the ball in the horizontal direction. So we have that Vy0 is equal to 0 as I have explained. When we look at the Vx0, the x direction, the motion in x direction, we have that x is equal to x0 plus Vx0t plus half of a xt squared. But we know that for the projectile motion there is no acceleration in the horizontal direction. So we have that this term go to 0. For x0, we can set the initial value of the horizontal direction to be 0. So we can set x equal to 0 here. It means that we have x0 equal to 0. And Vx0, we can set this Vx0 equal to the initial velocity Vi. Okay, initial velocity Vi. So initially we have only the x component of the initial velocity. There is no y component. That's why we have Vy0 is 0 here, but Vx0 is not 0 because this guy gives the ball the initial velocity in the x direction, which equal to Vi. So we have that x is equal to Vit, right? Or we have that t is equal to x over Vi. So if we put this t into the equation of y here, we have that y is equal to r minus half of g of x over Vi squared. So this equation gives us the trajectory of the ball. It means that it gives the coordinate of the ball x and y and the relation between x and y. Now, what we want next is the equation of the surface of the sphere. Okay, and that is easy from the elementary math class. You know that for the sphere we have that y is equal to we may write it x squared plus y squared is equal to r squared. This is for the sphere. Okay, this is for the projectile. Okay, this is for the projectile and this is for the sphere. And if for the sphere, if we rearrange the equation and write y is equal to square root of r squared plus x squared. Okay. To make it explicit, I may write this as the y of the projectile and this y is the y of sphere. Okay, and now what we must have is that at the same x position, at the same x, if you look at this position x, you must have that this y sphere is always less than the y of the projectile for the condition that given in this problem. So we must have that y projectile is always greater than y of sphere. Okay, and since both of them are positive, we can also write it as y of projectile square is greater than y of sphere square. Okay, we square this because maybe it's more convenient if we don't have or get rid of the square root sign here. Okay, so once we square the yp, we get that r square minus g x square vi square r plus g square over 4 times x to the power 4 over vi to the power 4 is always greater than r square plus, minus x square. This is minus sign, not plus sign. R square minus x square. Okay. Now, if we rearrange this equation a little bit, we will have that g of, you can see that we have r square on both sides, so it means that this r square cancel, and then we can rearrange these if we multiply by the minus 1 on both sides, so we have to reverse the larger sign here into the smaller, so we have that g times x square over vi square times r minus g square over 4 times x to the 4th vi to the 4th is less than x square. Okay. Or if we rearrange this again, we have that gr vi square minus g square over 4 of x to the 4th is okay, it's less than vi to the 4th. Okay, we get this relation by you divided both sides of this equation. not equation, this relation. So you cancel this term x squared, and this go to this term cancel, and this reduce to 2, and then you rearrange the equation, okay, by multiply by the vi to the fourth on the both sides of this relation. Okay, so this term we get vi squared is this vi the fourth cancel, and it go to this side. Okay, and then rearrange again to get that g vi square minus vi to the fourth is always less than g square over 4 times x to the fourth. Okay, so this is a relation that if we want the trajectory that the ball will not hit the sphere after it is kicked, the velocity of the ball must relate to the x position like this. Okay, if we have the velocity of the ball at the x position, the velocity of the ball, the initial velocity of the ball, okay, it will relate to the x like this. The meaning of this relation is that if we put, or if we kick, if this guy kick the ball with the initial velocity like this term must be less than the like side at all point x during the motion. It means that it will always less, if we have vi, that this term is always less than this for all x in all point of x during the motion. So we have that the trajectory of the ball will not hit or will not intersect with the surface of the hemisphere. Okay, so you can see that when x is increased, this term is increased. When s is increasing, this term is increasing also. So it means that this term will go larger and larger. But on the left side, this term remain constant because this is the initial velocity, not change with time. G is a constant, and I is the radius of the sphere is a constant. So this is a constant. It means that if we have this relation for the minimum value of x, and after that, when x is increasing, this relation will remain true for all value of x. If this is true for the minimum value of x, this is true at the minimum value of x. It means that it will always true for all value of x. So the minimum value of x is 0. It means that we can put 0 here. Okay. So at x equal to 0, we have vi square minus vi to the fourth is less than 0. Okay, this is the minimum condition. This means that if the left side is less than the right side at the minimum value of x, which is 0, it will always less than the right side when x is greater than 0. Okay, and from this relation, you can see that we must have that Vi square is greater than GR, right? If I put this minus Vi to the fourth, put it to the like side, and then divided by Vi square on both sides, we have this relation, or we must have that Vi is greater than GR square root of GR. Okay, it means that the minimum value of Vi is GR. It must be greater than GR to make the trajectory that not touch the hemisphere after it's kicked. So the solution is C. Okay.